Summary: streeting mechanisms. Gliding can be fun at any age. The majority can learn to safely go cross-country. The climate might change, but the physics of how the sky works will not. Therefore, my book is edition 1, and that won't change. Streeting. What do you know? Is there more than one kind of streeting? How do we identify streeting? Are streets always in straight lines? Do streets exist on blue days? Do streets drift? What is a street surge? How can a thermal suddenly get stronger at height? How do we best use streeting? Streeting. You need some wind and normally an inversion or two. Short streets and long streets. They often form over the sea too. There's power station streeting. Inversion-induced streeting. Blue day streeting. The thermals and separate mechanism for shear wave. Wave-induced streeting. Cloud shadow streeting. Hill streeting. Sea breeze streeting. And lattice streeting. And finally, gravity waves. Thermal structure then. We have a column expansion downwards. Between the rising and descending air, there will be an interference boundary layer which feels like flying over cobblestones. The warmer air within the thermal will be at a slightly higher pressure than the air around, and therefore the bubble will try to expand outwards into the descending air. This horizontal gust is only close to the central core, where there is the largest change of temperature. Power station streeting then. Here we have at the top our normal of the day cloud base. We have relatively drier air at height. The clouds generated by the high humidity coming out of the power station generally have a slightly lower cloud base. We effectively have man-made humidity. Of course, Smoky Joe has heavy air, and that will not extend into the street. But the cooling towers, maybe coal stacks or other buildings providing hot air, will all generate into the street, and it will encourage the humidity into a line. Air which is fully saturated wherever the cloud is formed will rise at will change its temperature at 1.5 degrees 1,000 feet. So we have some increased induced instability in the atmosphere at that point. Hence the air may accelerate above the cooling towers. Of course, downwind of the power station may be a wind shadow, which is providing another literal hotspot. So any combination of cooling towers, coal stacks and buildings are providing energy into the street. But the most important aspect is the humidity. And of course, in the morning, maybe as the humidity rises, it evaporates quite quickly, and that humidity, that line of humidity, streams out downwind of the power station. So it's basically a line of humidity which has the potential a little later on to develop into a street. Once the humidity has got up there, then the formation of a long or elongated column thermal effectively occurs. So each cloud cell will generate a column of sink. But just downwind of the first cloud, there's another cloud and thermal in its way, and that spills the descending air sidewards somewhat. Now this descending air may come down to 1200 feet or 800 feet or 500 feet. It will not necessarily go all the way down to the ground level. So cloud evaporation can cool the air by up to 4 centigrade. And so that makes the air at height very heavy, very dense, and it accelerates downwards. So descending air is effective and can drive the instability from below cloud base in what would otherwise be stable air. The lowering of the cloud base from normal cloud base is usually about 600 feet or so. And that works very well, where the normal cloud base, just above that, you can get wind shear, and again a drier environment, which feeds the overall street very effectively. The column thermals then, as they link together going downwind, may extend to below any lower inversion, or there might not be a lower inversion, in which case it extends all the way down to the ground, making a blustery surface wind. In this example, we have a lower inversion at around 800 feet. Therefore means that the cloud evaporation cooling the air by up to 4 centigrade makes the air descend effectively 2,200 feet below cloud base. Of course, it doesn't have to be a power station. It can be a hill. The air is driven up by the wind from the left, forcing humid air into an unstable layer. Here we have a visual understanding of the mechanism of streeting. Hot, humid air is coming out of the chimney, and it's only going initially straight up. It's then carried by the wind, and the edge of the humid air is evaporating. So effectively it's just the same as a cloud. On either side it is therefore descending towards the ground. And this cold air basically envelops the air that was minding its own business, which suddenly decides, whoa, it's far too cold for me, and up it goes. And initially we get this spiral effect. And after that, we get some structures of cumulus cloud. So now we're going to play this, and you'll see exactly what's happening. And you can see that the cells are generating themselves into a castellation, into a recognized street. The dark area under this streamer cloud, you can see it's streaming up. And that's air minding its own business, but then forced up by the cold air descending on both sides of the streamer cloud. So there we have the streeting mechanism visually. Castellations will develop, and in this picture here we can see that effectively the steam is dragged down by the descending air on the edge. So we know that the humid air coming out of the cooling towers should be warm enough and buoyant enough to go up. But because the water is evaporating so rapidly and making the air so cold, it's actually dragging itself down below the level of the cooling towers. Note here, the two thermal columns have rapid evaporation into stable air, and there's destruction of the classic vortex. They don't have the buoyancy to break Rayleigh's number, and so there is no thermal structure and nice fluffy cumulus kind of structure to the steam coming out of the power station. Note that this process is polluting humidity into a block of air to be carried downwind. So in this case, initially the thermal vortices are being driven off the cooling towers, but then they get to a much more stable environment where the thermal structure collapses, or the vortex structure collapses. However, it does continue to go up weakly, and then the structure of the air has changed again, so it goes into a new block, and in the distant power station on the left, you can just see the redevelopment of vortices going up to the highest level before again they reach another stable layer. So notice that despite the constant heat source, the air still does break initially into bubbles as they rise. This photo taken early in the morning, and a sharp inversion is obvious, with failure of the cloud to extend vertically, causing effectively a spread out effect part way up and at the very top, and a marked change of wind direction with height. Met streeting then. The Met Office usually only give one concept of streeting, and here we have a concept picture. So here we've got thermals generating humidity into the atmosphere. It reaches cloud base, it accelerates upward. As it does, it hits an inversion above cloud base. And that inversion is usually about 600 feet or so above cloud base. In other words, the tops of the clouds are going into much drier air and start to evaporate much more quickly, generating an increased rate of sink at the higher height. However, because the winds are also usually a little bit stronger and usually veer a little bit as they go up, then this descending air doesn't descend to make the column, it descends slightly downwind of the initial thermal source. The next thermal source coming up, though, slightly downwind of it, forces it to one side. And so we end up with a vortex ring formation of spirals, just as we saw in the video a little bit earlier. And we get like a cloud bounce. Of course, any other warm air going into the system is all held and retained there. You can get breaks in the street, of course, and you'll see that because there's a gap in the cloud. So let's have a look at streeting to scale then. So here's the self-regeneration of the street. Keeps on going and going and going. There's Greenland to the north, and this is streeting over many hundreds of miles over south of Greenland. Here we're having a look at Morecambe Bay, and this streeting is generated by the hills, where again the circumstances dictate that there's a very low level of very humid air, and that's being kicked up by the mountains there, and it's been feeding itself for some time. The sun comes up, warms it all up, and that line of humidity there that you can see in the middle of the screen has generated a long street. There's also a bit of parallel streeting generated. What is depends on the quality of your screen that you're looking at, but just under the dotted line is another one, street, which is miles and miles long, much more obvious or predominant than the street you can see in the middle of the picture, and that's been generated from the Welsh mountains. So here we have the wind below cloud base, a slightly stronger wind above cloud base. The clouds form, develop upwards above the inversion, and you have a little bit of subsidence as well maybe, which encourage a form of a spread out downwind. So instead of going outwards, it goes in one direction, which is downwind. The top of the cloud, as it evaporates, is actually forced backwards from its thermal source. If we look at top view then, and in this case we're keeping the winds in the same direction. So the wind at cloud base is straight down those green circles, which is the warm thermals coming up, the humid thermals coming up, and then just above cloud base, then the wind is a little bit stronger above the inversion. So the tops are blown left to right, but there's another cell in the way, so it falls slightly to the top and to the bottom of the screen here. And of course this descending cold air re-energizes the air that was coming up in the first place. So the leading strong thermal punches the highest and restricts the upwind downdraft, coupled with any significant change in direction of the wind above the inversion. So displacing sink distorts the vortex ring, distorts the formation, and the system becomes self-perpetuating. Street wibbles then. It is really important to recognize that this kind of streeting is not connected to the ground whatsoever. Wide cells without vertical ascent are generally bad news. So in this picture we're just going to clip forwards, and we can see that the two deviations in the street move with the street. So they are not connected with the ground whatsoever. So vortex streeting 3D then. We can see that the thermal cells are green, are coming up the middle. As it evaporates, the evaporated air, which is cold, cascades down the sides of the street, not all around the upcoming thermal. The general flow pattern looking down the street then. So the street at the moment is running into the display. As the cloud develops upwards, it becomes displaced to one side by the change in wind direction. As a result, the downwind side of the downdraft becomes broader and more dominant. The upwind side at height has to fight against the thermal within the clouds coming up. Taking this to extremes, we get the rotating storms and hurricanes. Remember that most rapid evaporation takes place at height, and more turbulence on this side interacting with the cloud edge. And so the analogy then is a jet of water sent directly up, but with a wind blowing across. Most of the water will fall more heavily on one side. So we know that normally, but not always, wind increases and veers with height. So in this example, we have a street with the wind at cloud base, which is going straight down the green blobs, which are the rising air. The wind near the tops of clouds, however, just above the inversion, has veered, and so it's now going to push the tops of the clouds more to the bottom of the screen. Now that means there is considerably more sink on the bottom of the screen in this diagram. The leading strong thermal punches highest and prevents the natural downdraft upwind, coupled with any significant increase and change in direction of the wind above the inversion. So here's my general flow, but the upper wind has got a crosswind to the street, and so there's going to be more sink on the downwind side. Again, a vortex streeting 3D then. You can see there's a great tendency for the right-hand screen to have a greater amount of sink than the left-hand side of the screen. And what's it look like? Well, it looks a bit like this then. How do you anticipate the strong thermal? When streeting, it is the widest cloud crosswind, or if jumping across street to street, the one where the cloud has climbed the highest. The sink line on the left of this cloud street is the sharpest line, therefore avoid it. But overall, this street could be drifting and it could be turning. Here we've got another picture. This is over Barrow, Morecambe Bay to the right, and again you can see the streeting is being generated by the wind with humid air being driven over the hills. This is down at Cranwell. The streeting starts from the east coast, some 40 kilometres away ago. Lattice streeting. Lattice streeting, if you know it's going to occur and plan for it, can be extremely useful. It means that the streeting is in two directions. So here we have a RASP forecast, 12 o'clock, Thursday 28th of May 2015. And it's a very unstable day, and the blue bits are in fact showers that are coming through, anticipated to be coming through. So that's 2 o'clock. Here is, sorry, that was 12 o'clock. This is 2 o'clock. And this is 4 o'clock. And we can see that the lattice streeting occurred right across the country by mid-afternoon. What does it look like? Well, it's a little like this. And it can be caused by several other interacting features, and it generates a wave-like bounce caused by the onshore wind, sea breeze. And the way that it occurs is, imagine where you set a ripple off in some water, but then you set another ripple off somewhere else, and where the two merge, then you end up with this lattice streeting. So here's conventional Met streeting in black, and then we've got this lattice streeting running the other way, almost 90 degrees, but it's not always 90 degrees. Sometimes it'd be closer to 60 degrees off. Street drift. Bear in mind the following. Wind speed increases and veers with height. Normally, but not always. Even at a gentle inversion with dry air above moist air, this change in wind can be quite pronounced. Hence the effects which we have just covered. However, the instability created with dry air over moist air with a strong trigger, like the wind blowing over a high hill or an island in the sea, causes a downwind ripple. This unstable street aligns with the upper wind, not what the LX is saying. And so the street will form across the lower surface area wind. It can be triggered by a particularly strong thermal, which develops a tall cloud, in which case the street will drift slightly crosswind. They can also turn slowly, normally clockwise, depending on the creative method. Note as the ground air temperature increases and raises or breaks the inversion, the entire street will collapse. Use it or lose it. Cloud bounce with hills. Here the moist air is forced up into the dry air and there's an inversion close to the hilltop. You'll see an active cumulus close to or on top of the hill, are followed by a series of cumulus streaming out for half a kilometre or 2 kilometres. However, the air underneath is invariably stable, and really, unless you're very high, you're not really going to be able to use that street. Streeting side view then. Climb if you need to in strong thermals and cruise the next strong thermal. Not below cloud base to half the height of cloud base in the UK. Get high and stay high for high speed cruise. Here we've got some broad streeting. The inversion is not far above cloud base, so they're not really generating a very strong and active street for us. Streeting, looking down from the top view. In the same way that as cloud base goes up, the distance between each thermal increases, the same applies to streets. Basically, the streets are about 3 times cloud base in terms of their width. Summary: streeting mechanism.